Hi, this is similar to I'm just gonna talk about what I learned today. Wait, hold on. So, so the main topic is today is B-tree, the time complexity in video insertion. Um, so did you really have to know about like the B-tree, how the B-tree comes from? So example, like the B-tree, the basically B-tree is a sieve, usually for the DB indexing. Like last video I just talked about what is DB indexing, what is record keys. So and the normal binary tree, binary for the binary search tree. I mean it's really great for this search, but the problem is that the time complexity is O log n. So what do you mean by that? It feels like linear. If you have 1,000 or 10,000, like 10,000 of array lists. So example, you have 10,000 value in arrays. The length, I mean like the number of the values, and you wanna get 99,000, like or whatever. You want to get like 10, like 100, let's say 1,000. But that means that you have to traverse the arrays that till you encounter 1,000 value. So those kind of thing is in the time complexity, like the algorithm view of this is called O log n. The reason why it is O log n, the worst case is O log n, is because the user put the n value and it will cost almost n based on its input. The time complexity is gonna be this almost same as the input. Example, if I draw with the graph, so that's gonna be O log n. What I believe of this is gonna be O log n. But the thing is that when you're trying to look at DB indexing, but the data is gonna be really huge. If you look at the Facebook and Google, their data is almost like over 10, like 100,000, over 100,000, of course. Maybe it's gonna be million, but to traverse until you counter in one example, if you put just 10,000 or 1 million, but 1 million data into just one array, it has to traverse it in until it counters the whatever value is. There's going to be more time complexity it is. So we now look at the binary search tree. The binary tree is very simple. You insert, example, you have let's say you have 3 2 1 2 3 2 1 4 5 6 7. It's gonna be three gonna be root of here, and 2 is gonna be left of 3 because 2 is smaller than 3, and the 1 is gonna be left of 2, left of 1 because 1 is smaller than 2. So that's gonna be like this, and the 4 is gonna be here, and 5 is gonna be here. Of course, 6 7 is gonna be, wait, I think this is right, or whatever, but this could make, this kind of thing can make into let's say 3 3 2 4, let's say 3, let's put 3 here, 3 2 and 4. It could like balance this kind of binary tree, can be balanced into like this, And when you're trying to search, example, you want to get the value too. The normal, let's say you have like this. So let's say you want to find the value 2. That means that you have to traverse in the array, you have to traverse until you encounter value 2, right? But in the binary search tree, you just have to compare the if it's small or not. Example, if the 2 is small, you go this part, and if t is 2, wait, no, this is wrong. This is clearly wrong. That has to be like here. Yep. If 2 is, so 2 is, this 2 is smaller than 3, so it's gonna be here. So if you look at this kind of colored node, we don't have to traverse this unnecessary the nodes. So based on that, we assume those kind of thing as this vector, this height. I think this height. Yeah, I think the height. Based on the height, let's say height is h. Based on the height, the time complexity is gonna be reduced rather than just the one rather than array. So it's gonna be O log, but like there's a 2. There's gonna be the height of here and n. Let's put like h. Gotta be more smaller. I might be not correct because I'm really new to time like algorithm thing. I'm really bad at algorithms. So this is how it looks like. But the thing is that even though this is pretty fine, but what if the best way is having like children's like this part, like bunch of children's to reduce the height. But the worst case is, what if there's only no children, there's only one children, like goes here and this part like this. And if it's like this way, and if you assume that you already traverse those kind of nodes, and you only didn't traverse only one node, that just means like you just traverse the array. So that's kind of worst case of it. I know the value is wrong, but I'm just trying to simplify it. So to handle those kind of issue, so the binary search tree, the worst case is O(n), just the array. So to resolve this issue, we just encounter B-tree. Let's say, so B-tree is kind of fascinating. You have to set a limitation of how many nodes get the keys. So you have to set up max key. For example, we say 3. So let's say the max key is gonna be 3. We insert 4, 5, 6. So this is node. We insert 4, 5, 6. So you already insert the 4, 5, 6, but you just basically encounter the node kids, the max length of node kids. We just define the limitation of node kids. So the primary key, the middle key is gonna be the parent node. So this is gonna be like this. The 5 is gonna be primary key, and there's no 5, and there's only 6 here. And now let's insert the 7. Since it just seems like binary tree, you have to just insert the value that is bigger than or smaller. You just have to compare it. The 7 is bigger than this 5 and bigger than the 6. You just go to next to the 6. And if it is 3, you go to this part because this 3 is smaller than the 5. And next is 2. And now we just encountered these cases already before. And we have to make this primary key as a parent node. We insert this 3 in this part, and we also have to separate and 2 or 4. And this is kind of how we do it. And also let's put 1. So that is how you create the B tree. So basically B tree, it really ensures that you don't have to make unnecessary the orphan. What I mean orphan is just like it's just like those kind of thing. You don't have to you don't have to make unnecessary node that doesn't have even single child. So the B tree is the goal is that to delete those kind of thing. So if you're trying to create the B tree, it's really different with the binary search tree. And also since this node, the keys is you can put a lot of keys on in the one node. That means that you will have more advanced time complexity, advanced like more quicker than the normal array or binary tables. Because example, you want to search let's say 8. Rather than traversing all of the thing, we just have to compare if this is smaller or not. The 3 is smaller than the 8 is bigger than the 3, and you have to go to the next part. And also the 8 is not between 3 and 5, and so it cannot be inserted in here. And now the 8 is bigger than the 5, and it just have to insert in here. And so if you look at how those works, so we just only traverse this node. So we just we just like traverse only this node, and rather than another unnecessary node here. So that's kind of like the good part of the B tree. But if there's more keys, you get more advanced and more quicker, but there's gonna be space complexity. But I'm not sure about space complexity because I'm really new to space complexity. I'm really bad at algorithm, those kind of stuff, because this is my first time, so. And this is kind of theory, and I implemented the B tree using the TypeScript. The making B tree was kind of hard because I really don't rely to the ChatGPT or internet search, because the art of the code from using the JavaScript is already enough. It doesn't use modern syntax like ES6. So if example is this search, I get search query index. Search query index is just like if you find index that is the smaller than the target, the query key is smaller than element, that is the index. But if it's not, just return the length of it, because the meaning of length is there's gonna be index of the child index. So if you find index, and it's gonna be or the recursion of it. The insertion is also the same. No, I mean like insertion is kind of hard, because what if the 8, this is already 4, right? And 7 has the primary key, and 7 is gonna be go here. This 7 is gonna be go here, and also and the 5 is already primary key, and you really have to care about this kind of splitting nodes. For example, you make a 5 as the primary key, and you make it as a parent. Since this is already there's a duplicated since there's a duplicated, how to say it, like the pointers of it, we don't have to really put the pointer like this separately. So if we have to merge it, we can just merge it like this. We can just wait. Hold on. Is this? I think like this part. But I forgot it. 5, 7. So 7 is gonna be here. I think this is gonna be more okay. So if you look at how does it work, example, I'm gonna show you an example. Let's say we insert, let's put like this part like here, pretty good, and let's delete this, and let's try to look at how does it work. And if you look at this kind of my face isn't showing, but whatever, and basically I just implemented this kind of bit tree. So 17, between 17 and this kind of big number, between those kind of number is gonna be here, and the bigger value is gonna be here, and the smaller than 17 is gonna go this part. So that's kind of really efficient binary of the bit tree, because we can just the height is gonna be the height is gonna be really fixed. The bit tree is the purpose of the bit tree is making the height also shrink enough to compare to the binary search tree. So this is it. Have a nice day. See you next time. Bye bye.